Hi everyone. In this segment, we will take a look at section point 5. The topic is called differentials, and we're only going to cover the highlights of this section. So it's going to be a very brief introduction to what is known as the topic of differentials. So basically, this is a technique to estimate the change in a function y equals f of x when we move a little bit away from x. So when x changes slightly, we call that slight change delta x. So when you go from a point x to a point x plus delta x, the question is how much has the function changed? So as x goes from x to x plus delta x, we're going to try to estimate how much the y values have changed over that interval. So to do this, we're going to use an estimation method. So typically what we're trying to estimate is really delta y, how much y has changed. That vertical distance change in y is referred to as delta y. So we're trying to figure out what delta y is. So delta y is the actual change, but we're going to estimate it by using something known as dy. dy is simply an approximation of delta y, and dy is basically a quantity that it will be determined using the derivative. So delta y will be approximated by dy. And what is dy again? Let's first remember, we know that dy dx equals f prime, right? So dy is a quantity that will be obtained using derivatives. And we know dy dx equals f prime. That's a notation. So I want you to imagine for a minute what would have happened in a way if you were to multiply both sides by dx. dy would be equal to f prime of x times dx, right? So this quantity dy, which is f prime of x dx, is known as the differential of y, and it will be used to estimate the change in y. So just to summarize, dy is referred to as the differential of y. So just to show you graphically what we're doing here, so the blue curve is y equals f of x. Here's the point x. Here's the point x plus delta x, so we moved a little bit away from the original point. At the original point, this is the corresponding f of x value. When you move a little bit horizontally to x plus delta x, go to the function there, this is the corresponding y value, f of x plus delta x. And so we have moved, this is how much y has changed when you go from here to here. F of x has changed from there to there, so that's a change of delta y. But basically what dy is an approximation of that using derivatives. And basically dy is, if you were to draw the tangent line right there, which is given by the pink line, so dy is basically this distance from here to here. So this is your dy. So we're estimating delta y using dy using a derivative. And as you can see, the further away we go from x, this line and this curve are getting more and more different, right? So basically, our estimation is going to get worse and worse because if we're using the tangent line approximation to estimate the change in y, so if you move a little bit in the x direction, this estimation is okay because delta y and dy, they vary a little bit. This is the discrepancy between them, right? Oh, this is delta y, this is dy. But if you go very far away, discrepancy is going to be like this big. So that's going to lead to a very large error. So this technique we're about to learn mainly works when you move just a little bit away from the point x and you're trying to estimate what happened. How did the y values change? Now, before we go to the examples to do the error estimations, let's just kind of practice this formula we just learned. So let's remember y equals f of x and dy equals f prime of x dx. If you ever forget that, just write dy dx is the derivative, right? And think as if you are multiplying both sides by dx, then dy equals f prime of x dx. So that's what we have over here. So if y is as the given function, what is dy? All you have to do is take the derivative of the right-hand side and put dx next to it. So dy is the same as f prime of x dx. F prime of x is 10x plus 3, so there we have it. So let's do this next function. If area function is given as as this expression. What is dA? So the formula, just different letters, but the same idea, right? So you're just going to do A prime of R dr. Instead of X, we have R in this case. So dA equals, differentiate the function with respect to R, bring the power 3 down, 3 over 3, they will cancel. So you have 5R squared plus 4R dr. Okay, so what if A was pi R squared? What would dA be? Again, the rule is you differentiate times dr. So dA will be, what is the derivative of pi r squared? Bring the 2 down, subtract 1 from the power, that's A prime of R dr. So in a sense, we're just finding derivatives right now, right? And instead of writing in the format dA over dr equals, you write the derivative, instead we're writing dA equals the derivative times dr. That's the main thing, but we know how to take derivatives. Therefore, so far there is really not that much new other than getting used to this notation of dy basically. Okay, so let's do this one last time. So if volume equals this equation, what is dv? So it'll be v prime of r dr, because again the variables are the functions in terms of r. So dv equals, differentiate the given function. When you bring the 3 down, 3's will cancel. Subtract 1 from the power times dr. Okay, so we just learned how to deal with this new notation, the differential of a function, the differential of the volume function. It's simply the derivative of the volume function times the incremental change in R or X, depending on what the variable is. So now let's do a couple examples to illustrate this through some application problems. So suppose we have a circle of radius 10 units. If the radius increases by 0.1, approximately how much will the area change? Also comment on the percentage change. So first of all, we need to remember what area of a circle is, which is pi r squared. And let's remember from the previous page, the differential of I is f prime of x dx. In this case, the differential of a will be, dA will be a prime of r dr. So dA equals, you differentiate pi r squared, which is 2 pi r times dr. Again, we're following this general formula. And in this situation, your radius was 10. The change in r dr is the same as 0.1. So basically know that we use dx and delta x interchangeably. So a small change in x can be represented by delta x or it can be represented by dx. Here we have a small change in r, so that's our dr. So that change is 0.1. So this is given as 0.1. Radius is 10. 2 pi is just a constant, so we're just going to plug those numbers in to get dA. So 2 pi times 10 times 0.1. If you multiply all of those together on the calculator and use 3.144 pi, you're going to get that dA. In other words, the change in area when the radius of a circle is 10, and if the radius changes by 0.1, the change in the area of the circle will be as follows. Just product of those numbers, which is 6.28. And finally, they also want you to do percentage change. And to get percentage change, what you need to do is, it's basically also known as relative change. You compare the change in area to the total area, and then you multiply it by 100 to convert the decimal into a percent. So we want to find percentage change, which will be dA over A. And so take 6.28 and divide it by the area, which is pi r squared, where r equals 10. 6.28 divided by pi times 100. And then you can put that into the calculator. Just be careful, because when you do this in the calculator, make sure you have on the bottom a set of parentheses to contain all of that. And that turns out to be 0.02. And to convert that into a percentage format, multiply it by 100. So percentage change in area is about 2%. So when the radius goes from 10 to 10.1, we're saying that the area of the circle will change. Because it's positive, it'll increase by 2%. Okay, so again, there is not that much happening, if you get used to this notation dA or dy equals f prime of x dx, and if you also get used to this convention that percentage change equals d of the quantity divided by the quantity itself, then really the problems are going to be very repetitive in this section. So we're going to apply the same rule over and over. So I'd like to do two more examples. Here's our example number 2. Okay, so use differentials to approximate the increase in the surface area of a sphere when the radius of the sphere increases from 4 to 4.1 inches. Also comment on the percentage change on the surface area. So first you need to know the surface area for the sphere formula, which normally I would give it to you. You don't have to memorize that one. That happens to be 4 pi r squared. And once again, let's remember our formula. Um, so dy equals f prime of x dx. So dy equals f prime of x dx. And we know that we use dy to approximate delta y. So we're trying to figure out how much the original function changes when x changes by a little bit. But in this situation, so if x, we have r, right? So we want to know how much surface area changes. So the change in surface area will be surface area's derivative times the little incremental change in r. And for this question, r is 4, and because it's going to 4.1, dr is going to be 0.1. It's the change, dr is the change in the radius. Going from 4 to 4.1, the change in radius is 0.1. So for this question, dr is 0.1 and r is 4. So what is SA prime for this question? What is the derivative of this quantity? Remember, 4 pi is just a number, it's a constant. So just differentiate r squared, which is 2r, and multiply that with 4 pi. So to determine the differential of the surface area, you got to multiply it by the derivative of the surface area times dr. So dSA equals SA prime times dr, and SA prime is 8 pi r multiplied by dr. That is the differential of surface area. So we're given r is 4 and dr is 0.1. Let's just plug those values in. R is 4 and dr is 0.1. Let's multiply them using a calculator. And you get a decimal value of 10.05. And surface area, the unit would be square units. So change in surface area would also be the same units if you want to put the units as square inches. And finally, so what we're saying here is if the radius of the sphere changes from 4 to 4.1, we're saying that the surface area of the sphere will increase by approximately 10 square inches. Okay. And what about percentage change? By what percent did the surface area of the sphere change? Do you remember how we find percentage change? So d of the quantity over the actual quantity. So d surface area, the change in surface area divided by the surface area. So that will give us by what percent did the surface area change. So we already know DSA, the change in surface area is 10.05, and divide that by, so I use one more decimal there, and divide that by actual surface area, which is 4 pi r squared, where r equals 4. So again, you may want to do the bottom separately, top separately, and then take the ratio. And if you do that, you're going to get 0.05, in other words, 5%. So we estimate that if the radius goes from 4 to 4.1, the surface area will change by 5%. Okay, one last question, and this one, it would be great if you stop the video first. After you read the question, try it, and then come back and check your answer. Okay, so the measurement of the edge of a cube is 15 inches with a possible error of 0.03. Use differentials to compute the propagated error In computing the volume of the cube, also comment on the percent error. So let me reword this question. Let's say for the moment that if each edge of the cube is 15 inches, suppose that that goes up by 0.03, from 15 to 15.03. By how much would the volume of the cube change? But because they did not say it increases by 0.03, they said it's an error of 0.03, it could be up or down 0.03. So the only difference between this problem and the last problem is that here, since we don't know if it's up or down, we're going to use plus or minus notation. If you like, you can just start assuming in the beginning that it's increase. Just try to solve the problem with that assumption. And at the very end, in your final answer, just put a plus or minus. That's basically it. So take a moment, please, and then come back, check your answer. So for this question, um, the volume of a cube is, if you assume each side is x, it's going to be x to the third power. And we're given that each side, x is 15, and it's going to change by 0.03. So dx is 0.03 because we don't know if it's plus or minus, so we're going to put both of them, plus or minus 0.03. It didn't say increase or decrease, it just said error. So we're going to consider both possibilities. So to find dV, how much the volume changes, right? That's what they want to know, the propagated error, how much volume changes in the volume. So then we're going to need to find dV. dV is v prime of x dx, so 3x squared dx. And now we know x is 15, dx is plus or minus 0.03. We're just going to multiply those together to find a change in volume, and just put the plus or minus up front when you get the final answer. And so volume has units of cubic units, so change in volume has the same units, cubic inches. So plus or minus roughly 20.25 cubic inches. So basically, again, the change in volume technically is delta V. But dV is a quantity using derivatives. It estimates the change in volume, and we find that the change in volume is approximately 20.25 plus or minus cubic inches. And how do we find percentage error? All you have to do is dV over V, the relative, the change over the total to find the relative change, the percentage change, right? So dV over V is what we want to find a percentage change or percentage error. Since dV is already known, 20.25, and divide by V, which is x to the third. What is x? 15, right? So put that denominator, and from there just simplify it. And we always multiply by 100 to get the percent. So if you move the decimal 2 units to the right, you're going to get 0.6%. So basically the change in volume is less than 1%. It's almost half a percent, slightly over half a percent. So if each side of the cube is 15 units, and if there's a slight change of 0.03 on the side length of a cube, and we're determining that the entire volume would change very, very little bit, it would change roughly by 0.6%. So there are actually two different kinds of problems in the topic of differentials. One is called linearization and approximating function values. In this brief version of this lesson, I didn't get into that. So we've mainly covered the types of questions where you figure out the change in y or change in any quantity they give you by using the differential to estimate that, and also by finding percentage change, which is dy over y. So those are the only types of problems for the current semester that you have to worry about. So, and that concludes the section.